This question is titled, What if my file names have spaces? And it's related to a problem that I see people constantly give the absolute worst possible answer. It ruins my entire afternoon when I see somebody say, oh, the script doesn't work because the file names have spaces. What's the answer? Don't put spaces in your file name. You don't even know how much of my own personal energy has been wasted just being irritated at that answer, because you know what? File names have spaces in them because they're tools that are used by human beings, and human beings think in terms of spaces. And so, in this question, rather than say why it is that we should rewind ourselves back to 1988 and only use file names that are 8 characters long with a 3-letter extension, we're going to talk about what do we do when we interact with real-world data, namely file names, and they happen to have crazy characters in them like punctuation or spaces or all that stuff that regular human beings use in order to be able to understand what's contained in the files that they've saved to disk. We're going to talk about the basic assumptions of the shell. We'll talk about one topic that I think is very interesting, which is the distinction between in-band and out-of-band encodings and how that leads to certain limitations you might have at the shell, and also fundamental API design complications. And we'll talk a little bit about what structuring is available in the shell, how we can get around this. In this session, or at least in this question, we won't be able to talk in too much depth about different means by which we can translate between env, argv, and standard in. There's quite a few additional follow-on topics we won't be able to get to. But why don't we jump right into it? And I'll give you a very simple example. Let's say I have 4 files on disk, A, B, C, D, E. Wait, 4 files or 5 files? Well, the last file is D space E. It's got a space in the name. And you can see I can view these files. I can even ask my Z shell to tell me how large these files are. And because I created them for the purposes of this example, they contain no data, so they have 0 bytes in their content. Great. Let's say I have a Git repository, and in that repository I have a couple of source code files and I have a couple of media files. So I have A, B, C, and D, E, except some of them are .py files and some of them are .png files. Again, I can use my Z shell and I can say, give me the size of the PNG files. Maybe this is some output from matplotlib and I want to see, is it worth storing this in the repository? Is this being used for some sort of visual test? Is this the reason why my checkouts are taking so long? Whatever the case may be. Now, it may be the case that I don't want to look at all of the PNG files, but I want to look at a subset of them. Maybe I want to look at them using some complex predicate provided by the find command. And the find command, as you know, is very powerful. We can do things like find things by some pattern. We can exclude things. We can say, give me all the files that are newer than this particular timestamp. There's so much we can do with the find command. And so what I want to do is I want to take the find command to find the files that are interesting, all the files that were created yesterday, because maybe that was when I last made a change to this repository, and given those file names, and just those file names, tell me how large they are. Now, what I can do in order to take the standard out of a program and connect it to the argv of another program is use a very common program called xargs. And I love xargs, and I use xargs all the time. Here's an example of how I might do this with a simple echo. Echo is just going to echo A.py, B.py. Those are just strings that are being echoed to the screen. They may not even exist as files, but I'm just going to output those. Then I'm going to have xargs pick those up, and xargs is going to run the file command on whatever input it's given. And so if I gave it a file name that didn't exist, it would then try and run file on c.py and say c.py doesn't exist, there's only c.png. Well, using that logic, what I should be able to do is I should be able to take my find command and pipe the output of my find command to my xargs. And it works perfectly fine with the .py, but it doesn't work with the .png. I get this weird error, cannot access D, cannot access E.png. And if you squint that a little bit, it looks like that disk use program, trying to figure out how many bytes are used by this file, doesn't know that D space E.png is one file name. It seems to believe it's 2 file names. Now, let's take a moment to think about how processes can communicate. Because there's a lot of different ways in which we can take the output of one process and put it into the input of the next process. We can pass information between different programs that are written. We have environmental variables. And if you have a child process it will inherit all the environmental variables of the parent process. You can kind of control what environmental variables are visible. You can set those. There's the argv, the actual arguments that you pass to the command line. And there's the standard in and standard out, the output that is generated by one file that's usually printed to your console, and the input that is expected by the next files. And so xargs is this intermediary between these two things. It's the intermediary between the standard out of one side of a pipeline and the argv of the other side. With the environmental variables, here you can see I have a variable x equals 1, 2, 3. I can invoke my shell, and I can see the state of that variable. And you know what? I can say x and y. I can set both of them, and I can see them with my env command. And one interesting and important thing about this environmental variables are they are strings. They are not numbers. They are not typed. They are just strings. And by strings, I don't mean Python strings. What I mean is how C thinks of strings. These are byte strings. These are null terminated strings. An environmental variable cannot contain a null byte because it is very likely that the underlying tool you are using to understand these environmental variables and to process them, namely libc, assumes that these are null terminated strings. And so there are some limitations for what you can have in your environmental variables. Now, whether the environmental variables are part of the operating system or part of your libc, and whether your libc is part of your operating system, well, on Linux, that's a little bit blurrier. In other operating systems like BSD, the connection may be a little bit stronger. Everything is intermediated by either libc. But it's the case that environmental variables are something that exist deeper than just the libc, but almost always it's the case that people use libc in order to interact with them. If you want to see a little bit about how this might look from a process standpoint, you can actually use a program called pstree in order to see what your tree of processes is. So you can see that sleep1 is running under this Z shell process, and as we go down this hierarchy, they inherit the environmental variables from before. It is the case that environmental variables are one way we can set flags that are out of band from some of the other ways. But if we wanted maybe a more in-band approach or another way to pass data, we can pass data by just passing command line arguments. A, B, C, D are passed to this program, and this program just prints out what it's passed. And more than A, B, C, D, usually you're doing something like, some flag, some argument that takes a parameter. And what you can see is argv is also a bunch of strings. And they're passed to these, and they're probably going to be null terminated strings because it's probably some libc layer in there that anticipates these to be null terminated strings, and so there's a limitation there. Now, the thing with standard in and standard out is they are not limited in that fashion. They do not have to be null terminated byte strings. They can be any characters whatsoever. The command line is orientated around the idea of processes generating untyped byte strings, just raw binary data, and then consuming raw binary data, where in many cases that raw binary data just happens to be human textual data that you can read and is encoded nicely and can print to the screen. But if you think of things like programs that zip, programs that encrypt, things like tar, they actually are passing raw binary data back and forth, and that is the fundamental assumption of the shell. It's all about dealing with untyped raw binary data. And some people don't like that, and they say, well, I wish I had a typed shell like PowerShell. We may talk about why that is a good idea in the environment in which PowerShell exists, but a very bad idea in the environment in which the actual Unix shell exists. But here what we're doing when we're running this xargs command is we're taking the output of find and we're piping into xargs and having xargs pick up each one of those lines of output and turn it into a command. Well, this arises an important distinction between what we can do when we need to encode data. Because we have this raw binary channel that's connecting these two processes. We need to encode that data. We need to tell the next process in this pipeline, hey, this is what I'm sending you, and this is what this means. And in general, there are two ways we can think about encoding data. The first is what we call in-band encodings, and the second is out-of-band encodings. And this is terminology that's borrowed a little bit from communications and signal processing, but it should more or less make sense. In-band typically means you have one channel and you do all your metadata and all your data in that one channel. So you need to find some way in order to distinguish them. Out-of-band means you have one channel for your data and one channel for your metadata, and you don't have to distinguish them because you know by virtue of which channel they're in, which they are. And you can think this general design is more fundamental than the shell. It's more fundamental than a programming language. You may have used things like FTP in past, and you may know that FTP has a separate control channel for control messages than it has for sending data. Well, this is an in-band, out-of-band encoding distinction. And when I say metadata for this in-band, out-of-band encoding, one of the things I should be broad about is this isn't just metadata as you think. This can also be structures. It can be modalities. Well, the problem with an in-band encoding is that it fundamentally has ambiguities. You can't tell which is the data and which is the metadata because they're jammed together in the same channel. And there are 4 general strategies for how you deal with it. Escaping, like in Python, if you have a single quote in a single quoted string, you escape. You say, the next thing happens to be something that you're not anticipating. Change your mode for how you understand this. As opposed to closing the quote, change your mode to understand this as a literal quote. There's quoting, which is you surround the text with something that says, hey, we're entering the special mode, like in XML with a CData block. We're entering the special mode, and then telling when we exit that special mode. But sometimes you can't really just do one or the other because you can think in a CData block, you cannot have a close square bracket, close angle bracket, because that wouldn't be disambiguatable from the actual close of the CData block. And so the CData block is actually kind of limited. It can't contain arbitrary character data. There is partitioning, and you've seen this before in another guise. If you think about pandas and you think about floating point numbers, what's happened with the IEEE 754 floating point standard is they've partitioned the space of all possible floating point numbers. Some of them are valid numbers, some of them are infinities, and some of them are nans. And nan means, oh, something went wrong. You divided by something you're not supposed to divide by. You multiplied by something you're not supposed to multiply by. What they did was they took all the possible bit patterns and they carved out some of them and said these can only ever be metadata, in the case of floating point, error codes, and the rest of these can be values. Whereas with integers, you can't really do that. You know, if your measure is always positive, you could say, oh, any negative value indicates an error code. But if your measure could be positive or negative, what value indicates something went wrong? And this is why, for example, pandas needs things like the capital I in 64 in order to have an out-of-band encoding for which of the integer values are masked. Because there's no way to partition the space of all the integers in generality to say, oh, these are special integers that represent something went wrong, and these are integers that represent a valid value. There's also prefixing. You can think if you've ever used a programming language prior to or around the C era, there's different ways for you to manage, strings. You can put the length and then say this is what happens next. And a lot of network protocols are this way. You say the next couple of bytes are this, the bytes after that are this, and you can prefix this. If you look at how Git actually stores data, it uses prefixing. It tells you how many bytes are in the underlying payload, and it has specific entries for what the type is and things like that. Well, the shell generally, as a historical remnant, assumes partitioning by whitespace. And unfortunately, some programs that you might use like make are really assertive about this assumption. In general, if you have spaces in your file name, it is difficult for the shell to disambiguate a space in the file name from the separator that's used to indicate where the next file name begins, because they're using this very naive partitioning approach to say, oh, spaces can't be in file names, at least not in the 8.3 era, but these days our file systems are a little bit more robust and our needs to store rich media, which have rich file names, are a little bit greater. However, file paths as raw byte strings can be partitioned in the sense that it is not possible on Linux to have a file name that contains a slash character or a null byte. And so the answer to what if my files have file names is you need to find an unambiguous in-band encoding. You only have a couple of choices for how to disambiguate. The choice that you're going to choose is partitioning because you quoting and the other things aren't really understood by any of the shell programs. And what you can do is you can choose a better partitioning character, one that you're guaranteed will never, ever, ever, ever show up in a file name, namely a null byte. And what you'll find is most of the commands that you have, that you use at the command line will understand this. Print 0 means print these file names null terminated. Xargs-0 means assume my input is null terminated file names. Sort has a Z flag, which means assume my input is null terminated. And as you start to look through all of the programs that you use, you'll discover that if they work with file names, they all understand this. But the ambiguity problem is way more general than you might think. Here, if we look at our find command, we can see which find command we're using, and we're using just our regular bin find. Well, how do we determine where that find command actually is? How do we determine what happens when we type find? Because if we had a file in our current directory called find, is it going to use that find or is it going to use the bin find? And what you might know is there exists an environmental variable called path that gives the colon-separated paths that you search through in order to determine where something is. And so if I add my present working directory to my path, suddenly my find command that I'm going to run is no longer the actual bin find, but the one in the directory that I created on these two lines. What if you have a path that you want to add to your search path and it has a colon in it? Because I told you, and I brushed this off, oh, they're colon separated. What if there's a colon in it? You're stuck. Dead stop. There's nothing you can do. You cannot, in 2000 and whatever this year is right now, you cannot have a path in your search path for commands that has a colon in it. Because there is no escaping mechanism, there is no partitioning mechanism, there is no mechanism to disambiguate between this colon separates these paths and this colon is part of the path. And this is a mistake. This is a complete flaw in the design of these tools that has not been addressed because for the most part, how often does that really happen? But you can see that once you can spot this in-band, out-of-band ambiguity problem, well, you can't not spot it. It is all over the place. For example, a much more modern tool like Docker, you can run a Docker container and you can mount specific directories in that Docker container. And the format for that is source directory colon the destination directory with with another colon and some flags. What if you're mounting a directory that has a colon in it? Docker, which is a very modern tool, does not allow you to mount a directory with colons in it because it would be unambiguatable or would be ambiguous with, is this the source? Is this the destination? And when you start looking further, even tools that you use every day like Xarray data array, here's an Xarray program that takes a block of data and you can look up on this coordinate system values at a particular, that don't exist here in linearly interpolating. So here you have x measured from 0 to 10 with 3 steppings. So it'd be 0, 5, and 10. You could say, give me the x values at 0, 1, and 2, and do a linear interpolation. And you do that by passing a method parameter. But you look up the data you want by passing that as a keyword argument. What if in your Xarray data array you have a axis, a dimension called method? You can't look it up. This is an absolute flaw in this API. This API is broken because you can't have a parameter here or you can't have a dimension here that's called method and then use the API. You have to go find some alternate means. And the reason for this is they didn't disambiguate between the data, what you're looking up, and the metadata, the mechanism by which you're doing the interpolation, whether it's linear or not. You can't not see these once you start seeing one or two of them. And this is why, if you ever think in Python why you might use star args or star quarks or the positional separators or the keyword argument separators, in some cases they can be used to force a disambiguation to avoid this problem. There is not a real solution for this problem, except you can use symlinks, and that's typically what you'll do. So you take this directory and you symlink it to a directory that doesn't happen to have an underscore in it, and the path is symlink aware. So you could do something like that. That might work. Or if you are very clever, you might use something like BRAP to take an existing file and mount it with a different name so you don't have physical artifacts. But we're not going to talk about BRAP just yet. It is going to be a big topic when we talk about isolation and containers later. Now, I really hate this when you have a long command at the command line and you put backslashes because it's so ugly and you move things around and you have to add them and whatnot. You know what? The shell is not that bad. It does have some out-of-band structurings. One out-of-band structuring it has is typically your bash shell or your Z shell will have regular arrays. And so every time I'm writing a really long command, I'll put the arguments in just an array, like a Python list, so I don't have to backslash terminate them, and I can easily comment them out like this, and everything just works, and then I'll paste them into the command line. There we go.